Welcome to Chapter 5, Forces. So this chapter is really getting into the swing of things. We're taking some of what we've learned before with vectors and x and y components and all that, and acceleration and motion. A is acceleration here. And we're combining those into a concept that actually we experience every day and that causes acceleration, and it's what's known as a force. So there's 8 main concepts in this chapter, and I'll just give a quick run through before I go into more detail on each. The first one is Newton's second law. Hopefully you've learned that at some point. It's just force equals mass times acceleration. Don't forget the unit of mass is kilogram, although there are other forms. The unit for acceleration is meters per second squared, and again there's other forms, but those are the main ones. And the unit for force is whoa. Okay. Anyway, the unit for force is a Newton. Spelled like this, named after Isaac Newton, who's a brilliant man, and abbreviated with capital N. A particular force that we're going to deal with, although there are many more than just this one, but a particular force is weight, which is just the force of gravity acting on you. And weight, which is the force of gravity, F, often written as F little g, equals m little g, where little g is still an acceleration, right here, but it's the acceleration due to gravity, and that's 9.8 meters per second squared. Oftentimes you'll see negative 9.8 meters per second squared. That just means that a direction has been defined, and that's like step 7 here. I'm going to talk about that in a sec. And in that case, down would be negative. I like to call down positive, but as long as you pick whatever one makes you comfortable, just stick with it. Net force. So usually there's more than one force acting on an object. So the net force is the sum of all the forces acting on it. This symbol, if you haven't seen it in calculus yet, this means the sum. So if you have 5 forces acting on an object, you figure out the individual the individual accelerations from each force, and you just add them up. And often we'll have forces acting at an angle, and so we can separate those forces into x and y components and do a net force in the x direction and a net force in the y direction. If you remember projectile motion, like that, there is a net force in the y direction called gravity, but there is no net force in the x direction, and so it doesn't accelerate in the x direction. When you're dealing with the net force on an object, you only include forces acting on a particular object in that equation, and I'll go into more detail on that later. So when an object isn't accelerating, that means either no forces are acting on it, or all of the net forces add up to 0. So you may have a force being cancelled out by another force, or multiple forces being cancelled out by other multiple forces. And when doing any of these force problems, I'm going to require that you do a free body diagram, FBD, and it must be drawn correctly, and I'll show you how to do that, because on the free response problems in the AP exam, you're going to be expected to know how to do that. Another type of force we deal with is the force of tension, which is basically the force that a rope or string exerts on an object. Tension in an ideal rope, which is basically the situation that we're going to deal with most of the time, if not all the time. There are a couple problems where we have to treat the rope as a real rope, not an ideal rope. But an ideal rope has no mass and it doesn't stretch out. And if that's the case, then the tension is the same all along the rope. Define a direction of motion, positive or negative, like I talked about for gravity here, for each axis, the x direction and the y direction. And as I'll explain when I talk in more detail about this step, if the rope changes direction, which can happen if you have a rope wrapped around a pulley, then you'll define a direction along the entire rope. And finally, I'm going to show you the geometry of net forces when a block is on a ramp. Alright, let's get right into it. 5 minutes in, we've got 10 minutes for this video left. Number 1, Newton's second law. So Newton was like I said, a brilliant person. Tried to escape the plague, which is a scary thing back then because we don't have the medicine. They didn't have the medicine that we do now. And while he was hiding away on his family's farm, I think that's where he went. He, I guess, was a little bored and just decided to really change the world with some thought experiments. And one of them was an analysis of forces. And he realized that if you have a mass and you apply a force to that mass, then that mass will accelerate, and it will accelerate in a proportional manner to the force. You double the force, you double the acceleration. And as I said before, the unit for a force is a Newton. So that's pretty straightforward. This was kind of hidden for a while actually, because for example, if you slide a block on a floor, the block slows down and stops. And friction. If to say the block started, I don't want to draw this too confusing. Let's say the block started sliding to the right. Jeez, it's huge. So say when I draw a force, I'm going to draw it from the center. So here I'm just saying the block's going originally to the right. As you know, friction is going to slow this down and stop, but we didn't always know that friction was a force, and so it was thought that objects just tended to want to come to rest. That was their natural state, and so that's just what was happening, which kind of hides this whole proportional aspect to forces. So anyway, that was a good revolution in forces. Although I think Galileo had a part to play in that as well. Second one, weight is a force of gravity. So if you have an object, then there's a force of gravity acting on the object. That is the interaction force between two masses. As we're going to learn, it's not just that the Earth is pulling down this mass. This mass is also pulling up this mass is pulling up the Earth. So let me draw the Earth here. There's a big Earth. And that's also known as Newton's third law. Which I probably should have put that as a concept, but it doesn't really play a role in any of the problems that you have in your book. But Newton's third law, I'm sure you've heard it before, is equal and opposite. So if the Earth pulls a block down with a force of gravity this strong, then the block pulls the Earth up with the same force of gravity. Anyway, long story short, this force is acting towards the center of the Earth, and this force, the block pulling up the Earth, is acting towards the center of the block. And that's where you can start defining your direction. So if you want to say that way is positive and that way is negative, then this would be a positive acceleration. If you switch that, this would be a negative acceleration. But regardless, at the surface of the Earth, this is how high the acceleration is. That changes if you go higher up above the Earth, or if you're on a different planet, or just out in space. Your acceleration due to gravity depends on the two objects. And there is an equation for that, which is in a different chapter. Yeah, so we'll deal with that for now. Net forces. So let's say we have a block here, right? We have a force of 8 newtons going that way, and a force of 5 newtons going that way. What's the net force on this? Well, F net, and let's write this in the x direction because these are x direction forces, they're horizontal. That's the sum of force 1 plus force 2, so that's 8 newtons. Well, let me just write it out. We'll say F1 plus F2. We'll call this F1. That's supposed to be an equal. And we'll call this F2. So that's going to be 8 newtons plus negative 5 newtons. I did negative because I have to define a direction of motion. And let's call this way positive and this way negative. So the net force equals 3 newtons. That's all it really is. But as you'll see when we deal with problems where the forces act at angles, we got to do components and all that stuff. And you only want to include forces acting on a particular object. So let's say we have the ground and a block here and a block on it and a rope pulling this block. Here's a rope. And let's say there's friction between the two surfaces. I'm really getting into some advanced force stuff, which you're going to see in chapter 6. So don't let all of this confuse you right now. You don't have to worry about this so much right now, but I'm just trying to illustrate that you only include the forces acting on a particular object. So let's say this is object 1, and this is object 2. If we want F net on object 1, we got gravity, Fg, pulling object 1 down. We got, again, we don't need to know this really for this chapter, but we got a normal force. We'll say minus Fn, because we'll call up negative, minus normal force. And if there's friction here, and the block 2 is being pulled by the rope that way, block 2 is going to drag block 1 along, and in order to do that, there has to be a force of friction that way to drag it along. So plus, oh, and we don't want to stick this in here because these are y direction forces. Now again, don't let all this confuse you yet. I'm just giving you an example. X, force of friction, right? Now some people are inclined to say that the rope is acting on 1, so you'd say plus force of the rope, or in other words, force of tension. But this rope is only acting on object 2, and so you don't put that. You only want the forces acting on object 1. We can do separate forces, a separate net force equation for object 2. Each object gets their own set of net force equations. So that's really the only point I was trying to illustrate. I don't want you to get bogged down by all these details here because that's chapter 6 stuff. I just wanted to show you about what forces to include on each particular object. And this will be the last one I'll do for this video. When an object isn't accelerating, you have two options. So here's block. So let's say this block isn't moving. That could be because the force of gravity acting down is being exactly balanced out by the normal force of the floor pushing up on the block. So you'd say F net in the y direction equals Fn or Fg minus Fn, which equals 0 if those forces are equal. So it's not going to go through the floor and it's not going to go flying up into the air. And you could also say F net in the x direction is 0 if there are no forces, or let's say there's a force tension here and an equal force of friction going back, Ft minus Ff equals 0. If those two forces are equal, then the net force is 0. There is no acceleration, It's basically stuck there. It's like a tug of war where the two teams are exactly the same strength. Alright, we're at the 15-minute mark. I'll continue with number 5 in the next video.